So we're going to start in a few minutes. So please remain seated and yeah, for the opening ceremony. Thank you. See you soon. 시작해야겠죠? 오셨으니까. 네, 예. 그렇게 해야 될 것 같습니다. 네. 네. Okay, so good morning, ladies and gentlemen. Welcome to Postech Signature Conference. Postech has launched this new international conference series to lead innovation and promote collaboration in science and engineering. So this year, we will focus on the overarching topic, quantum technology and science. So I'm Gil-Ho Lee, Associate Professor in the Department of Physics at Postech, and it's my honor to serve as a moderator of today's opening ceremony. So recently, quantum technology, considered as the next generation of technology, has emerged as a significant field of research and development with the potential of revolutionize several sectors of the society. So this conference aimed to bring together scientists, researchers, and engineers from across the globe to discuss and explore the latest development, challenges, and opportunity in the field of quantum technology. So I'm very excited to have the leading expert worldwide in the field of quantum science and technology. And thank you all speakers and audience for joining us today. So to welcome audiences and speakers, Professor Sung-Geun Kim, President of the Postech. 인사 그냥 소개만 하는 거였습니다. 네, 네, 네. Sorry for the confusion, sorry. And also, Kang-Deok Lee, Mayor of Pohang-si. Seung-Tae Lee, Director of Division of Science and Technology of Gyeongsang-Buk-do. Here, thank you. So first, President Sung-Geun Kim will give us his welcome remark. Okay. President Kim, the floor is yours, please.
Good morning. It's a real pleasure to welcome everyone here for our Postech Signature Conference. Whenever I'm in the presence of physicists, I get reminded of a fond memory of one of my friends in France who happens to be a physicist. I met him a long time ago in a conference. I introduced myself as hi, my name is so-and-so. I'm a chemist. And his quick reply was, that's okay, nobody's perfect. So that's a typical spirit of physicists. I hope it prevails in this meeting too. Well, everything that I wanted to say as a welcoming remarks is already in the brochure. So instead of repeating myself, I want to share some memories of my own quantum mechanical journey. Quantum mechanics is probably the coolest thing I've ever studied, learned in college. So after I took some quantum physics and quantum chemistry courses, I wanted to learn more. There were not many books, actually, that satisfy some of students' appetite. But I heard a rumor from the physics department that some of the graduate students were trying to print an illegal copy of quantum mechanics textbook by Landau and Lifshitz. And it was illegal because it was written by Soviet scientists, and Korea was a staunch anti-communist country at the time. So this was done in a secret way, and getting a copy of Landau and Lifshitz was very difficult. It was a covert operation to get a secret copy of Landau and Lifshitz, but it was I eventually ended up getting one, and it was so satisfactory to flip the pages and go through the materials, which was very impressive. Of course, I didn't understand much of it, but it was a very interesting experience. This bunch of grad students actually had a 1+1 sale too. They gave out classical mechanics textbook of Landau and Lifshitz to whoever bought the quantum mechanics textbook. So it was a fun memory. Now fast forward 20 years from that, I was a faculty member in chemistry department at Seoul National University. I was subscribing to Physics Today. And in 1990s, maybe perhaps late 1990s, there were a series of very nice articles in Physics Today that dealt with Einstein-Podolsky-Rosen hypothesis, Bell's inequality, and quantum entanglement. And I read that as a hobby, was very interested. I knew it would lead to something like a Nobel Prize someday, which it did eventually. But I never thought that it's going to lead to any practical applications. But we never know, because the very quantum concept of quantum superposition is the basis of quantum computing these days. So one day, quantum entanglement may lead to something practical as well. I hope my French physicist will forgive my ignorance as a chemist. As for the topic of today's conference, I'm not shy to say that Postech is very strong in quantum technology, and it's one of the strongest areas of Postech, although we do recognize the unmistakable presence of star scientists from elsewhere in Korea. I'm indeed very happy that Postech came to host this conference, and I just hope that everyone enjoys the conference itself and their stay in Pohang and Korea. If I can borrow a line from a popular movie series, may superposition and entanglement be with you. Thank you.
Thank you, President Kim, for his warm welcome. Okay, the next, I would like to ask Mayor Lee for his remark. Mayor Lee, please.
오늘 포스텍 시그니처 이 컨퍼런스 2023 개최를 진심으로 축하합니다. 우리 포항에서 국내외 양자 전문 과학자와 연구원분들을 모시고 양자 기술에 관한 국제 컨퍼런스를 가지게 되어 매우 뜻깊게 생각합니다. 아울러서 이 컨퍼런스를 준비해 주신 포스텍 김성근 총장님을 비롯해서 대학 관계자 여러분께 감사드립니다. 또한 참석한 신전문가 여러분께도 환영과 감사의 말씀을 드립니다. 이번 컨퍼런스는 양자 분야의 국내외 저명한 전문가들이 모여서 양자 기술의 미래에 대해 토론하는 매우 중요하고 의미 있는 자리인 것으로 알고 있습니다. 양자 기술은 여러분 아시다시피 바이오는 물론이고 제조, 반도체 등 미래 산업의 모든 분야에 혁신을 불러올 궁극적인 핵심 기술로 일컬어지고 있습니다. 여러 국가에서 지금 집중적으로 양자 기술 개발에 박차를 가하고 있고 우리나라도 2035년까지 민관 공동으로 3조 원 이상의 투자와 2,500여 명의 양자 전문 인력 양성을 목표로 해서 양자 지원 정책을 수립하고 적극적으로 추진해 나가고 있습니다. 우리 포항은 철강 산업이라는 중공업 시대를 선도한 것을 지나서 이제 미래 먹거리인 신약 개발, 2차 전지 같은 미래 신산업에 대한 선제적인 투자와 정책 추진으로 과학기술 선도 도시로 변모해 나가고 있습니다. 양자기술 분야에 있어서도 포스텍, 막스플랑크 한국 포스텍 연구소 등에서 연구를 진행하고 있고 미국, 일본에 이어 세계 세 번째로 구축된 4세대 방사능 가속기를 통해서 양자기술 연구를 뒷받침하고 있습니다. 우리 포항시는 아토초, 위상양자, 응집물질 연구 등 세계적 수준의 양자기술 연구를 적극 지원해 나가고 있습니다. 앞으로도 차세대 양자기술을 선도하기 위한 도전을 계속해 나갈 것입니다. 이러한 양자기술의 성과와 발전은 다양한 분야의 미래 신산업에도 활용되어서 함께 시너지 효과를 낼 것으로 기대됩니다. 모쪼록 인류의 새로운 가능성과 기회를 창출할 차세대 양자기술 연구개발에 힘쓰고 있는 국내외 모든 분들의 노력을 응원하면서 오늘 컨퍼런스에 함께해 주신 모든 분들께 좋은 시간 되시기를 기원합니다. 감사합니다.
Thank you, Mayor Lee, for the kind word. Thank you. 감사합니다. Next, I'd like to share the remark from Chalu Lee, the governor of Gyeongsang-buk-do. Although he was not able to join us today, he kindly sent us the recorded video to congratulate the Postech Signature Conference. Okay.
반갑습니다. AI 도지사 이철우입니다. 2023 포스텍 시그니처 컨퍼런스 개최를 진심으로 축하드립니다. 포스텍 김성근 총장님과 관계자 여러분들 고맙습니다. 또 주제 발표와 토론에 참여해 주시는 국내외 전문가 여러분께도 특별히 감사드립니다. 시대를 막론하고 과학기술은 국가 경쟁력의 핵심 원천입니다. 최근에는 첨단 산업을 중심으로 글로벌 패권 경쟁이 더욱 심화되고 있습니다. 특히 양자 과학기술은 미래 산업 분야의 혁신을 주도할 게임 체인저로 세계적인 주목을 받고 있습니다. 그런 점에서 오늘 컨퍼런스는 더욱 뜻깊습니다. 국내에 저명한 전문가 여러분들의 지식과 경험을 공유하고 양자 기술의 방향과 미래를 조망하는 의미 있는 시간 되길 바랍니다. 정부도 양자 기술 분야를 12대 국가 전략 기술로 선정하고 지원하고 있고 최근에는 관련 법안이 국회 본회의를 통과하면서 산업 발전을 위한 제도적 기반이 마련됐습니다. 경상북도 역시 세계 최고를 지향하는 연구 중심 대학 포스텍과 함께 대한민국 양자기술 산업 기반 조성을 위해 노력해 나가겠습니다. 이번 컨퍼런스에서 경상북도의 정책 방향에 대해서도 다양한 제언을 해주시면 적극적으로 지원해 나가겠습니다. 감사합니다. 반갑습니다. AI 도지사 이철우입니다.
죄송합니다. Yeah. Okay, thank you very much, Governor Lee. Although he was not able to join us, he kindly sent us the video message. Okay, so lastly, I would like to ask Professor Jae-hoon Kim, who is the chair of this conference and also chair of the Department of the Physics at Postech and also the director of the MPK Korea, for the welcome remark, please.
First, welcome, and on behalf of organized committee of this conference, I would like to really welcome to all you guys, and I first thanks to come to here in this morning, and I remind me actually that this building was built in 2007, and that time actually I organized the first conference held in this building. So I remind me about 16 years ago. But anyway, this time and I organized another conference. Actually, this is a Postech Signature Conference, and this is second Postech Signature Conference. Actually, this is the university really supported this conference. as a like a landmark conference of the university. So then actually this is second Postech signature conference, and the first one was like a medical science topic, and the second this year the topic is about quantum technology. So anyway, recently, like quantum technology is some kind of a hot issue, and in the like not only like physics, also in the engineering, and also in the like a government and even society. It reminds me. I think it is something like a very early, like something like 1920s or 30s about like first time IBM created some kind of computers. But I think this is about the time, about like 1920s, 30s in early time for the like development of computers. But anyway, in the case of like quantum technology, seems like Google and IBM developed like they announced like really running quantum computer. But as you know, there are lots of like hurdles and many challenges we should solve to really like realize the quantum technology. So this is why we organize this conference, because okay, we are focusing on the most like more like a science and also like applications, because I believe present quantum technology development is not enough for us to really like use the quantum technology. So this is why like some kind of scientists really need to do real research, like basic research, to overcome some challenges and like hurdles to really realize the quantum technology. Actually, the quantum technology society really like interested in quantum technology because they really think this is really like they can use it, but actually this is a little bit far away. So this is why we really need to do basic research to break down such kind of like hurdles and the challenges. So anyway, so this is why this conference we made a conference, and we gathered all like expert scientists and also engineers and all like researchers get together, and we discuss about the recent topics about like quantum technology or quantum science, to really like discuss about a new modern like a recent development of the scientific topics and also like engineering parts. So this as introduced by the Professor Lee, and this conference is aimed to gather together and discuss and solve such kind of quantum science. And then I hope this conference not only provide an opportunity to share like cutting edge research and discovery, but also contribute to the development of the advanced of the quantum science and the technologies. Actually, I look forward to product and engaging conference, and wish it memorized as one of the most enjoyable conferences. Finally, I really close my welcome remark with my deep and great thanks to Postech and MPK and APCTP and the IBS for most important thing is the financial support of this conference. Okay, thank you.
Okay. Thank you, Professor Park. Okay, thank you all very much for the upbringing. Okay, so before proceeding the scientific session, we will take a photo, a group photo. Okay, so we'll President, Mayor, and Director of the Division of Science and Technology, and all the invited speakers, and please come to the platform. Thank you. Okay, thank you all. And this is the end of the opening ceremony, and we will start the scientific session shortly in 5 minutes. Okay, let's see you soon. Thank you.
Good morning, everyone. First of all, I would like to extend a warm welcome to all the attendees of Postech Signature Conference of 2023. My name is Hee-Deuk Shin, a faculty member of Physics Department at Postech. And it's an honor to serve as an session chair of as the session chair for this segment of our program. In this session, we have an exciting lineup of distinguished lineup of speakers, two distinguished plenary speakers, and two invited speakers. Each talk will have 5 minutes of Q&A time, so you can ask any question at the time. Let's commence our session, and I would like to invite our first plenary speaker, Professor Philip Kim at Harvard University, to the stage. He obtained his PhD degree at the University of Berkeley in 2009. Oh, sorry. I'm so sorry. He obtained his PhD at Harvard University in 1999, and he became a faculty member at Columbia University in 2002 to 2014, and he joined to the Harvard University at the Department of Physics in 2014. I'm so sorry for the confusion. Please welcome the first plenary speaker.
Thank you very much for the chairman. That nice introductions, and then I'd like to thank the organizers to invite me for this nice conference. It's an honor to be the first speaker of the conference, and so it's kind of good to be back to the Postech. I think I visited here multiple times, many times, but every time it was kind of quite exciting all the way. So I'm going to start with this the conference discussing about this engineered quantum materials for the quantum technology. I think this is nicely tag on to the introductory ceremony that we heard. Especially, I was really excited to hear that this new president of the Postech, Professor Sung-Keun Kim, discuss about this entanglement and possibly the technology based on that. And I'm sure that we'll learn a lot throughout these 3 days of the conference about the current status of the quantum technologies. In some sense, today that I'm going to discuss about the basic materials that may allow that those kind of quantum technology. I think that's kind of topic. The cover slide shows some of this hint. These are some of the quantum materials, and then there's some of the engineering structures you can see. And out of this one, we want to kind of learn some of the new physics that may allow this the further development of the quantum technology. That's basically an essential part of my talk I'm going to share today. Of course, the quantum technology we heard a lot of times nowadays, and it comes with the various different aspects, sensing, the computing, communications. I think all these topics we touch upon 3 days of this symposium. But as all these things to be realized, we need some sort of platform to just enable the technologies. And often that in terms of the devices, we need the materials to realize this type of the technologies. And often that those kind of materials that enable the quantum technology, and broadly speaking, we can call the quantum materials. And my story is about this, the quantum material story. And particularly that engineering quantum material that enable the quantum technology. What is a kind of good example? My favorite choice of the best example of the quantum material is in fact the semiconductor heterostructures, which has been developed in past probably half century or so. And techniques such as molecular beam epitaxy allows us to put down the atomic layer by layer in a sense that you can control the multiple of the layers in the really atomic scales and up to that really macroscopic scale into this that you can see that these wafers. And that allows that a lot of the modern technologies, a lot of the electronics and optoelectronics, indeed based on our ability of the growing those kind of quantum structures. But also, this type of structures enable the new science studies. Notable example is a fractional quantum Hall effect, one of the most strongly correlated electronic system that we can create it, can be discovered into this electron confined in the heterostructures, and that has served us there are a lot of exciting study past probably 2 or 3 decades also. Often that this fractional quantum Hall effect, hover that very unusual quasi-particle called the anyons, and this anyon, which actually doesn't exist into the 3D, that provide us some of the intriguing way to use as the quantum technology. Let me start from that as a kind of good example. Any quantum particle in the 3D, when you exchange these 2 identical quantum particles, there is always quantum statistics. It dictated that we can just categorize this particle either boson or fermions, depends on their exchange statistics. However, once you confine the particle in the 2 dimensions, such as the good example that I showed in previous slide, electron confined in heterostructures effectively work in the 2D, other possibilities possible. For example, when you just kind of exchange these 2 particles, it doesn't have to come into the either boson or fermions, which actually dictated by the sign of the wave function changes when you exchange this. In fact, it comes with some phase differences and some discrete phase differences. If the system is non-degenerated, if the system has a degenerate states, those kind of the braiding or the exchanges actually bring this particle to a completely different particle in another degenerate state. Often those kind of things is what we call the anyon, and it only exists in the 2D. And we have the very weird statistics, which can be useful for some of the technological applications, such as it's been discussed that especially when you have the so-called non-abelian anyon, which means when you braid this particle or exchange it, the particle turns into something other ground state. Turns out that theorists comes around this non-abelian anyons can be useful for just braiding the operation, which can encode the quantum information into this entanglement that delocalize in the space, such that as long as you just protect those kind of existence anyon, the information is topologically protected, right? Obviously, those kind of non-abelian anyons can be used as, if you have many of them, just kind of keep braiding them and just use as one of the interesting way to realize very robust quantum computations, often called this the topologically protected quantum computing. Now, of course, to realize those kind of things, we need the anyons and show that whether these type of the anyon, especially non-abelian anyons, can exist. This is, in the past few years, I think community just to show that those kind of the platform may exist, at least theoretically, and just try to come up with some of the way. And one way is this fractional quantum state I just mentioned. They are appearing the electron confined semiconductor heterostructures, especially those kind of fractions called this even denominator state, such as 5/2, is kind of the theoretically proposed that this contains a non-abelian nature of the anionic the excitations. And the other the platform that people actually argued about is that say that if you combine with a superconductor with some of the other topological materials or that semiconductor with a strong spin-orbit coupling, in certain conditions, you should be able to realize those kind of non-abelian anyons or so-called the Majorana states in there. And there has been quite of efforts that push into the realizing some of this type of the platform using various different quantum materials in the natures, right? I'm going to actually discuss a little bit about this type of the forefront of the quantum material development, especially using the so-called two-dimensional materials. So let me start with this, the first topics. Can we actually realize this fractional, the quantum states, especially even denominator states, aiming for the non-abelian anyon development? If I just make the conclusion at this point, you will be disappointed. I cannot present anything about the concrete result or even just kind of getting into the really deep science, but at least I can just report back that kind of solid and interesting progress that community can make now. Past few years actually quite kind of interesting landmark years, especially that it comes with the anionic physics. Part of the reason is now the gallium electrons that confine the gallium arsenide got evolved quite a bit, And now the people start kind of demonstrating indeed at least the abelian anion braiding can be possible. Here's a good example that this was done by Manfra's group at the Purdue University. They just developed this highest quality of the gallium arsenide heterostructures with a very good control of the Coulomb interactions. And they start kind of finally see that 1/3 of the fractional quantum of states, which is known to be harbor the abelian, the anions, and just kind of they form this electron interferometry. And out of this, the Fabry-Ferro interferometry, they start to see that this intriguing the phase shift in this interference pattern, which actually contains information about the non-abelian anion, the abelian anions kind of signs here, which is kind of 1/3 of the charge. About the same time, in 2020, this is the French group beautifully show that in this experiment, they show that indeed this is electron versions of the Hongul-Mandel experiments, where that just measuring the cross-correlated noises. Also, they show that the anions that they have has also fractional charges there. Again, the one step further kind of step the progress into the braiding demonstration of those kind of the abelian anions. Of course, these are kind of good progress. However, the issue here is, again, to get into the next level of the showing very similar experimental non-abelian anion, you have to just produce a really robust non-abelian anion states, which is an even denominator state, which has been a little bit of issues onto the gallium arsenide-based fractional quantum effect. Now, of course, there comes kind of different stories. There are different ways that one can create a two-dimensional electron system, especially using so-called Van der Waals materials. Starting with the graphene, which discovered about 20 years ago, that the set of the community, the set of the scientists in this community also developed a way that one can create a two-dimensional electron system: graphene, boron nitride, transition metal diachalcogenide, and so, right? Almost we've been seeing the past 20 years, a lot of the rediscovery of this layered material, Van der Waals layered material. One used to just grow them or extract them down to the monoatomic layer or monounit cell thicknesses. They start kind of behaving like the electrons confined in 2 dimensions. And furthermore, depends on your choice of the bulk crystal you start with, you can create a various different property of the electron system based on the semiconductor, superconductor, sometimes a charge density wave system, sometimes topological insulator. Basically, that there are a lot of different kind of the two-dimensional system can be created by choosing the right set of the bulk system. Furthermore, you can, in principle, stack them together, like the semiconductor heterostructures. You can form this, the quantum heterostructures. Often that you can combine the materials with the different properties. Those kind of materials start to show rather different type of properties that differ from this the crystal. So idea is maybe we can just use this material for new platform to realize quantum technologies that we can realize. The technique that one can just kind of make the heterostructure is reasonably simple, and most of the cases you can just cleave this crystal down and restack them together using this Van der Waals stacking method, which has been now well developed. Although this method cannot produce a really scale up the wafer size of these devices or that the samples, but this method is effective enough such that you can just create a few tens of micron size of sample that at least we can study about the physics in there, right? And combined with this type of the materials that with this device fabrication techniques that can be applicable for those kind of small size of sample, now one can produce various different devices. For example, graphene encapsulated in between the boron nitride, simplest the heterostructure you can imagine. Graphene has the two-dimensional electron system, and boron nitride here act like the just the dielectrics around there. Already there, that the mobility that you can get in the graphene is extremely high, almost kind of approaching to the mobility of the electron that you can get in the gallium arsenide. Allows us that you can study quickly some of the interesting correlated physics, including fractional quantum effect. Here's the data that they taken by, I believe, the Corey Dean's group a few years ago, showing that as a function of magnetic field, you see that this dark line stands for the quantum Hall states. Integer quantum Hall 1 to 3 is there. But you can see that a bunch of this, the other lines that correspond to the fractional quantum Hall. More importantly, those kind of even denominator quantum Hall state appears in this bilayer graphene encapsulated boron nitride, and very robust way up to the very high, this reasonably strong land magnetic field. I think this type of the robust presence of the fractional quantum Hall states, especially in the even denominator state, immediately can bring this excitement. Might be this simple graphene encapsulated in boron nitride serve as kind of interesting material platform to realize that those kind of device that realize in the gallium arsenide. Now, just to do that, what you can do is just copy down the same method has been done in gallium arsenide. For example, that we can just first build up the heterostructures. Here the graphene is encapsulated between boron nitride, but then on the top and bottom we can just put a few layers of the graphite, which serve as a metallic layer. Once you pattern it, that can be used as this local gate. So simply that as you just make this device in the gallium arsenide, you can build a very similar device. Here's a good example. Through this device fabrication technique well developed, here is a final device. So here is a piece of the graphene and connected by the electrode, but on the top, the contrast is a little bit bad, but you can, if you believe me, there is this cut through the top gate, which define this local gate on the top, which again, by just biasing this local gate, you can just control how the electron can they move around this pathway, because in quantum Hall states, electron only move through the edge state defined by this local gate, right? All this gate can put some part that you can deplete the electron, some part you put into different quantum Hall states. Whole point here is in this mechanism, so what I can control the electron pathway around here. And especially this essential part is, this is basically electron cavity. We can create this Fabry-Pérot oscillation with a magnetic field. You can see that those kind of Fabry-Pérot oscillation start kind of oscillating, which we can measure by the conductance measurement. So clearly, like the photon, that in the photonic cavity or Fabry-Pérot cavity can produce this interference, we can just generate the electron interference that using this graphene type of electrode. Up to here is nothing too special because this can be done in gallium arsenide. Now, in the gallium arsenide communities, push this into even fractional quantum Hall states, right? One can make the second generation of this one, kind of even further the improvement. For example, that now this is the gate. Instead of we just put on the top of the layer, we can just kind of suspend this gate using the air as a gate dielectric to make the dielectric properties extremely pristine and clean, right? And in that way, you can just increase this the efficiency of this interferometry. As you see here, that when we measure the quantum Hall state, we have the nicely defined integer, right? But then in between that there's a lot of this wiggle. This is not a noise, but if you just kind of zoom in there, these are all kind of correspond to each of the fractional quantum Hall states. Because of this, the interferometry is extremely clean. You can see that the interference actually evolved through this the different state, different type of this oscillation. Already you can see that there is a phase jump that I just mentioned into the gallium arsenide experiments. It appears much more regularly, which means we can control this kind of even better. Even further, that as you through there, this ion bomb oscillations start kind of make the frequency doubling, which actually is a very unexpected properties. I think this is kind of demonstrating the technology we can just kind of install into this 2D materials becomes kind of quite the promising that one can eventually push into this fractional quantum Hall states, especially even denominator quantum states. Again, my story onto this part stop here because it's a really developing story. This paper has not been even just written up, but shows the status where we are, just using this the pristine 2D system that we can realize in graphene. One nice thing about the graphene is it allows that some of the experiments which could not be done into the semiconductor structures. For example, that fractional quantum Hall states, one can just think about, can I just kind of hybridize this fractional quantum Hall state with something else, or quantum Hall state with something else? One interesting thing that we can just think about is, well, we can just, for example, hybridize this quantum Hall state with superconductor. What will happen? Now, this type of experiment is rather difficult to realize in semiconductor. Part of the reason is, usually quantum Hall state requires a strong magnetic field. Superconductor doesn't like the strong magnetic field. So to make these things kind of combine, I need a special superconductor which can withstand a reasonably strong magnetic field up to a few Tesla at least, right? And those superconductors, such as niobium, niobium nitride, molybdenum, and those kinds of superconductors, usually it's very difficult to evaporate onto the semiconductor. Even if you do so, they form this Schottky barrier. So making good transparent superconducting contact has been very challenging. However, graphene does not have the band gap, which means in principle you can make those kind of junctions possible. So that experiment was done in my group when Professor Giro Lee, that next speaker and the moderator of this conference, was kind of working with us. And this is kind of device he made. So it's a graphene that is an niobium nitride, make this contact, and once you apply the magnetic field, there is an edge state forms and send these electrons and holes around this edge state. But if you just zoom in this superconducting lead, which actually designed in such a way it's kind of really narrow and finger shape, you can be following way. Along this the superconducting finger, there's quantum edge states kind of turning around and transport through that near the interface between superconductor and the quantum the channel. However, this finger is so thin, those kind of states going in this direction and opposite direction start kind of hybridize through this superconducting order parameter. And this is precisely the theoretical proposals that can be made, one can make this localized Majorana states at the end of this superconducting wire. Basically, we can realize those kind of chiral edge state kind of hybridized by the superconductor throughout this platform. So that was kind of the idea, and this actually worked it out beautifully. And not only just worked it out, nowadays that we can just kind of put not only one finger and make the another finger and try to kind of make these two localized Majorana start to talk to each other. Throughout that, we can measure this Josephson current, which actually depends on to the quantum Hall filling parameter, and those kind of experiments can be done. And furthermore, one can actually push this experiment even further, such as that one can improve this the graphene quality as well as a junction between superconductor. It is possible now just kind of do this experiment and not only integer quantum Hall, but in the fractional quantum Hall limits. And this is kind of quite a recent result we get. Here is again the superconducting the lead, the contact, which is very thin, and this is quantum Hall states we can set into the graphene. We can especially measure so-called this downstream the chemical potentials in the quantum edge state, which contains information that how the electron is converted to the hole through this narrow superconducting wire, which contains the information that how well we can create those kind of non-abelian anion at the end of this tip. So we just kind of show that indeed measuring those downstream the chemical potential, which can be converted in terms of the resistance. For example, that when we start to see the quantum Hall effect sets in, that nu equal 1, nu equal 2, integer quantum Hall, as well as this fractional quantum Hall effect. On the same condition, if you measure downstream the voltages or the chemical potential, we start to see that integer quantum Hall develop this nice, well-developed negative voltages, but furthermore, this fractional states developed even stronger negative voltages, which means that it actually converts the electron hole much more efficient way in this fractional quantum, compared with the integer quantum Hall states. Theory tells us that those kind of behavior, the very robust, the downstream negative voltage or even stronger downstream voltages is precisely related how that electron then couple to this the downstream hole in the superconductors, the forming these Cooper pairs. But if you just kind of think about there are various possibilities, instead of you just convert this the anionic particle to the real particle, the real electron in the hole to combine to make the real Cooper pairs, if I just kind of directly couple this two anionic electron and the holes to form this the unusual the Andreev pair, you expect to see that if this process is win over, basically that at the low temperature fractional quantum Hall cross Andreev refraction is much more stronger. Indeed, our experiments that we show that fractional state shows even stronger the cross Andreev reflections. They prefer that this scenario of the creating those unusual the bound states, which actually is a very first step to show that indeed we can create these non-abelian anions at the end of this quantum wire. So again, this is another example that simply that we started with this simple two-dimensional system, combining with other strongly correlated systems, such as a superconductor. One should be able to make the interesting material platform, which might be useful for the anionic braiding eventually. All right. But we don't have to stop into just the graphene, right? Or we don't have to stop into just encapsulate simple graphene. We can stack them together with much more complicated structures. Here's another example. Here, that this is about 5 or 6 different heterostructures layer. One graphene, but there is another graphene is separated by the thin boron nitride. If I just make this boron nitride really thin, this will serve as a good tunneling layer. But if I make this boron nitride thick enough, there is no tunneling. However, electron in the top and bottom layer can be correlated still throughout the Coulomb interactions. One should be able to measure very interesting phenomena, such as so-called the Coulomb drag throughout this type of device. Or you can just kind of completely replace the graphene with some other materials. In this example, that we replace the graphene with a moly diselenide, tungsten disulfide. It's a P-type semiconductor, N-type semiconductor. So that forms simply PN junction. You may say that PN junction is well known, except that this is atomically thin PN junction, right? And you may ask, what can happen in there? So this type of the device also can harbor that the interlay exciton, which can be quite useful, that I'm going to give you some of the example in a moment. Perhaps that one of the most advanced device in my group ever made is something like this. Here that I think I forgot to count, but probably 9 or 10 different layers kind of stack them together, which actually has various different type of properties. And aim here is by just constructing these vertical structures of the Van der Waals system, one should be able to make quite intriguing the functional device out of that. Right. Okay. So with this, what can we study? So one thing that I want kind of briefly discuss is, can we actually realize a very robust macroscopic quantum state in this two-dimensional materials heterostructures? I should define what I mean by the macroscopic quantum state. What I meant is really some of the state you can just take the look with your naked eyes, right? Something like the superconductor or the superfluidity, or in some cases the cold atom, the Bose-Einstein condensation, right? All of these things actually shares the one interesting commonality. The robust macroscopic quantum state is nothing but just the condensation of the bosonic degree of freedom. Here, the bosons that I'm talking about is not just fundamental particle of the boson, but it is a composite boson, often made of this kind of even number of the fermions can couple together, right? So idea here is once you create any fermions that can put them together into the bosonic form, ground state, that as a bosonic ground state, we can create the sum of the condensation, and that can be quite a robust condensation, so we can realize as a ground state. In fact, this type of the idea has been quite widely used in our colleagues in the AMO communities, right? Here that you start with the diatomic molecules, and by just controlling the Feshbach resonance, one can form this composite bosonic molecule. And this depends on the control of the interaction. You can control the size of the composite boson relative to that this interbosonic distance. Then you can just create this condensation into the more of this BC type of Bose-Einstein condensation type of the part through this weakly bound bosonic condensation, which often we call this BCS type of this phase transition, and has been widely studied into this cold atom community. One interesting part is, can we actually realize very similar idea into the solid state? There are good, interesting candidates. There are many candidates. In fact, one of the interesting candidates is using the exciton. For example, when you have the semiconductor shine the light, you can excite the electrons into the conduction valence band to the conduction band, and this remaining the hole in the conduction band tied to the valence band tied with the coulomically coupled with this electron in the conduction band, they form the exciton. Although exciton, as the name indicated, the excited state, which actually have the finite lifetime, it's certain condition if you can make this exciton live really long, you can envision that many of the exciton can eventually form this quasi phase diagram. And already theorists, they calculated out if the exciton is long-lived, one can just expect to see that this phase diagram consists of, again, if the exon density is small, then exon will go to the BC type of the transition, but exon density is large, then you will get the BCS type of the transitions, right? Can we realize those kind of things in the solid state? Well, there has been some of the efforts, especially again using semiconductor heterostructures. If you have the two quantum well, and if you just kind of excite the exciton in one of the quantum well, and then if you bias the quantum well, of course this exciton will dissociate it, electron and holes in there leaving the different layer, but nevertheless is a two layers very close by, so they still coulomically intact form so-called interlay exciton. In interlay exciton, of course, wave function overlap is suppressed. They tend to live long, right? And if you just pump enough of the excitons into the system, they may condense. Indeed, this type of experiment has been realized in, about a decade ago. Here is a good example by the Butov group in the San Diego. Beautifully demonstrated that indeed if you make this quantum well, pumping up the number of the exons there, they start to kind of form some spontaneous coherent states in there. Very first step to realize this the exon condensation. While this is an exciting development, you see that there is some of the issue here. First of all, this is semiconductor structures. Usually, strong dielectric constant screens that charges quite effectively, such that exon binding energy is rather small. To realize those kind of exon condensation state, one has to go to the extremely low temperature. Second, the quantum well cannot be really, really sharp, so they have only just kind of some overlaps between this electron hole wave function, leading to the lifetime is reasonably short, something like the hundreds of the nanoseconds. Is there a way that we can improve that? Again, 2D materials can just do a little bit better job. For example, in the 2D material, that we can just get the various different type band gap by choosing the different materials. Here that I'm showing the band gap and alignment of the transition metal dichalcogenide semiconductor. Some of them becomes the P type, some of them becomes N type. We particularly choose moly diselenide, tungsten diselenide, form this atomic scale, atomically thin the heterostructures. The device example I just showed a few slides ago, right? And turns out once you just have those kind of structures exciting the electron and hole, exciting exciton in one of the layer, quickly this exciton will dissociate it in tri-layer exciton will be dissociated and form this interlay exciton. Once you form this interlay exciton, you can just control their energy by just applying the electric field in the vertical direction, and they can control their lifetime by just controlling the separation of the electron hole by applying the gate voltage, and lifetime can be even just approaching the half microseconds, much longer than one can realize into the conventional semiconductor heterostructures. Using this type of excitons, and there are a few groups that start kind of realize the very first step, demonstrating the exon condensation. One of the examples I'm going to share here is here. So in this particular case, we just put the top and bottom gates onto the semiconductor heterostructures, and one can create the inhomogeneous electric field across the sample. Exciton is charge neutral, so the gate simply just controlling the electrostatic cannot control the exon positions, exon energy. However, if you just put the matching gate and changing the electric field across the system, you can control the energies and you can create a trap. Indeed, by just kind of changing gate voltage, we can have the no trap. Here is even anti-trap or the trap. You can see that physically in the location along this the gate region, we can accumulate more excitons in there. It turns out once you accumulate more exciton, their energy and their width or their emission width got strongly kind of affected by just changing the exon gate, exon density, as you demonstrated here in the one-dimensional exon trap. As you change the laser power to create this number of the exon density, we see that both of the line positions, which actually related with this exon density due to this strong dipolar repulsion, and their emission width, which actually related with this lifetime, got strongly affected and strongly changes. Carefully studying this exon density and exon at their kind of lifetime allows us to at least draw some of the phase diagrams of the expected exon phase diagram I just showed before, right? For example, by just looking at this, the density versus line width, we start to see the line width is suddenly turns on certain density, which means that some kind of strong phase transitions and strong unbinding of the external, the very strong trend of the external unbinding event happens. Using this one, we can just kind of construct the external phase diagram, at least a part of that. And this phase diagram tells us that where that strong sudden unbinding of the exon is happening, and that's basically getting to this phase diagram. This is exon density and the temperature. The phase diagrams are kind of going outward like this. Compare with what is a theoretically expected exon binding, the exon diagram, we start to see that at least this unbinding event follow through this degeneracy line. So in a sense, we have this quantum exon densities there. And the sudden kind of unbinding event actually matches very well with what is expected so-called Mott transition, which is basically boundary between the BCS, BC to the BCS boundary in the kind of lowest temperature. So at least again, it's not just a smoking gun evidence of the exon condensation, which is macroscopic ground state. At least we start to see that kind of just kind of good progress getting to the understanding of this exon, and furthermore, how to they manipulate this type of exons around. Now, one may ask that, assuming that if the exon is really, really condensated and getting to the ground state, what do we expect? In fact, there is a really nice model system realize those kind of state. That is not using semiconductor gap, but it's actually using Landau gap. If you have this bilayer of the electron system and applying the magnetic field, there will be Landau level forms, right? And this one can use those kind of Landau level between the Landau level, this Landau gap, as you're just kind of creating the exciton across it in some sense. Well, here's a kind of interesting example that if I just apply the magnetic field and fill up this the two electron, the gas, the layers with the density such that given that this magnetic field, these two Landau levels in the top layer and bottom layer is partially filled. In terms of the quantum language, this is kind of boring because a full Landau level will give you the quantum states, right, with edge transport I just mentioned. Partially filled Landau level is kind of boring in a sense. It is just kind of bad metal, right? You don't expect something unusual things happen. However, when you have this complementary field Landau level between these two layers close by, especially if the layers are very close by, the electron on the top and bottom layers start kind of correlate each other through the Coulomb interactions, and such that electron is on the top, the electron in the bottom layer will push it away and form effectively that exciton-like the structures, and mathematically those kind of correlated electron state in these two Landau levels precisely map into the exon condensation state in semiconductor structures, right? So what do you expect in those kind of things? By the way, this experiment was realized some years ago, and the experiment actual demonstration is beautifully done in the following way. One beautiful experimental demonstration is if you just connect this two layer into one side, such that if I send the current to the top layer, it returns back to the bottom layer. So this is what we call the counterflow geometry. So let's say the electron is hole is flowing to the top layer, and current is returned to the bottom layer in this direction. If the bottom layer is filled with the electron, of course, the electron will going against of the hole. So if you just look at there, current is flowing this way, but particle, the hole moves there, electron moves there. If the electron holes are coupled into the exciton and they condensate it, basically exciton is transferred from this side to there. And since this is exciton condensation, like the superfluid, there is no resistance you can measure into this system. So experimentally, this is kind of weird situation, right? Each of the layer, top layer and bottom layer, is bad metal, right? Half filled, partially filled Landau level. But once you connect them and send the current in the opposite direction, top and bottom layer, it's actually carry the current without dissipation like the superconductor, right? So that's basically what we expect to see. And indeed, this was actually done in the experiment about 20 years ago using gallium arsenide, right? So now you see that my trend. I think how many minutes I just talked about? 30 minutes now, right? Getting to 35 minutes, right? All the example I showed you is basically kind of just a copy of what has been done in gallium arsenide, right? So what do you expect to see here? Well, we can just do the same thing, right? So take the very similar gallium arsenide structures, but replace it with the graphene, and we just repeat that experiments, right? What is the advantage we have here is, again, that electrons in the graphene is much more highly confined, right? And that we can put this graphene together very close by, because boron nitride is a very good dielectric with a very strong the gap between this the two layer suppress the tunneling between them. Therefore, that we can put this the two layer of the electrons to something like the almost order of magnitude smaller distance than what can be done in gallium arsenide. Therefore, the exciton energy here will be much higher, so which means that this is much more robust. So this robustness allows us that we can map this phase diagram of the exciton condensation by just looking at this counterflow resistance. So that's basically this result. Here, this is temperature and magnetic field. I'm just showing you that here counterflow resistance, and the red is finite counterflow resistance. Dark blue is basically zero counterflow resistance. You see that as I change the magnetic field, there's an interesting phase diagram between condensation to the non-condensation state appears there, right? If I make the several cut through this constant magnetic field, especially when you just look at the high magnetic field, counterflow resistance is finite, but actually drops like the rock at a certain temperature, goes to zero, right? If I just don't call this is counterflow resistance, but just resistance, what do it look like? It look like superconducting transitions, right? Not surprisingly, in this high magnetic field, basically the exciton condensation follow through more like the BCS type of this the condensation. And as you just move into low magnetic field, magnetic exciton distance becomes large, and that becomes kind of more like the BC type of the transitions. Therefore, what you are seeing here is experimental mapping of the BC to the BCS transitions into this system. So that's kind of something that we can see excitingly, right? All right, so up to here is what probably has done in the gallium arsenide, but we just do the detail and just really mapping out. But we can go further because all this quantum state is much more robust. We can just push this experiment even further. There's one wrong statement I made in kind of 2 minutes ago. I mentioned that partially filled Landau level is boring, but that's completely wrong. In fact, if you go into the extreme quantum condition, means the low temperature, high magnetic field, partially filled Landau level is where that you start to see the fractional quantum states, all these anions, right? Indeed, once you get into the kind of right conditions, we start to see that this is an integer exciton condensation that kind of I just discussed. But in between there's other condensation state appears. It looks like the kind of wriggle, but more important part is at some point you start to see that this zero resistance appears. That's basically where that the new condensation. Some of the condensation is trivial. This is a 1/3, and that 1/3, I think 1/3 and 1/8, 3/8. I think those kind of things state is something more related with a single particle like the states. But 2/5 and 3/7 cannot be explained with the single particle states. And that's kind of something that can be only explained in terms of the coupling of the anion state or composite fermion state in top layer, composite fermion state in bottom layer. And with that, we can explain some of these condensation states. Furthermore, this condensation state is not just kind of appearing one phase space, but by just tuning this gate, those kind of the unusual condensation state shows as a line of the states, which means it's not only the coupling between the composite fermion, but nearby composite fermion where the anion excitation is there, we can make that as just coupling at the condensation state, and that's basically what we start to see that in this kind of devices. Furthermore, that once you just get into the more complicated graphene system, such as bilayer system, repeat this experiment, phase diagram becomes enormously rich. But important part is, out of this phase diagram where we have a lot of the more control in this system, we start to realize a bunch of the different type of the states which never been seen in the single layer quantum states. Suddenly we start to have the whole zoo of this the unusual particle, I would say anion pairs, start to appear in the system, which allows us kind of a lot of things we need to study that first and see whether there's any implications using those kind of the particle or robust kind of quasi-particle for the some of these kind of devices. Okay, I have kind of 3 minutes. 5 Q&A, but I don't want to eat up to too much Q&A. But certainly I cannot stop my talk without talking about this twisted the layers, because that becomes kind of so popular. One thing nice about this layered system, especially Van der Waals layered system, is you can just stack them together. But even with the same layer, when you stack them together with so-called this twisted angle, there is another yet capability of the creating the engineering the electronic structures by just using these quasi-periodic structures. This type of the study was really popularized only 5 years ago when the group of the Pablo Harrier at MIT demonstrated that if you just put the two graphene layer with the 1.1 degree, which is called the magic angle, they start to see that graphene becomes suddenly insulator, which is very unintuitive in the single particle pictures. And often this insulator is called correlated insulator. But then, soon after, they found that if you just adopt the correlated insulator, the graphene becomes a superconductor. It actually shook the field quite a bit. Part of the reason is it's very difficult to imagine that why the graphene can be superconductor with such a small amount of electron density. Turns out that previous theoretical approaches and following the theoretical approach tells us that flat band formations by this Moiré engineering is really key. And that actually launched the huge efforts in these communities, such as not only just kind of bilayer graphenes with the twisting, the magic angle. There are a few different ways that creating very similar structures, such as you can increase the number of the layer, 3 layer, 4 layer, 5 layers, or you can just kind of stack different materials, such as bilayer graphene or the TMDs. Or they comes with sometimes a superconductor, sometimes a generalized magnetism, some other correlated state, but not share is basically this Moiré engineering allows us to study about different type of the structures or different way of the creating electronic structures. It does, I think those kind of structures, let me skip this one, doesn't have to even stop at this the simple system. Nature allows us to kind of have the strongly correlated materials such as cuprates, such as bismuth, strontium, calcium, copper oxide, which is a well-known cuprate, also comes as a Van der Waals system. Turns out this, you can just get down to the one unit, monoatomic unit cell, which is about the nanometers. Furthermore, with the proper the techniques, one can create these heterostructures out of it. And here is a good example. We can just kind of cleave in cold temperatures and just stack this the visco together with a very thin layer with, say, some twisting angle. In this particular case, it is 45-degree twisting angle. And then those kind of the twisted device shows a very unusual the physical properties, such as that you have very suppressed the critical current, but nevertheless it's very uniform. More importantly, those kind of the special twisting angle start kind of give us that not only engineering electronic structures, but also engineering the superconductors at the spectrum, especially Andreev bound state spectrum, allows us that something like the unusual superconducting order parameter, such as a D plus ID type of order parameter at the 45 degree. And those kind of the superconducting order parameter allows us also create some interesting devices, such as the Josephson junction shows this the fractional Shapiro steps, which actually probably related with something in the next speaker's the talk. Furthermore, those kind of this the unusual order parameter landscape give us that the control the superconducting diode effect or non-reciprocal current effect by just kind of trained by the flowing the current into the system. So I'm sorry to kind of speed up this last part, but the whole point I'm trying to make is now this the combined with the twisting angle, the engineering, suddenly that there are a lot of different kind of phase space we can explore to create these materials with various parts. So let me end with kind of following slide. So in past probably 20 years or so, ever since the discovery of graphene, the community started to realize there are many other two-dimensional systems with various different properties. Furthermore, you can start kind of combine them together to create the rather interesting heterostructures, such as, for example, combined with say superconductor with a ferromagnet. What do we expect? They are competing each other, right? Over the time, a lot of them can be studied, and a lot of them can be started to utilize for device implications. But more exciting part is now, on the top of that, we can actually also use a twisting angle as another knob to engineer the system. There, that we have even continuum of the possibility of the explorable phase space. I think that's kind of make what this field is rather exciting and give us the hope that some of the system can provide a really solid material platform to realize quantum technologies. Okay, so I think that's all kind of I want to share. And here's my students and postdocs that allows this work to kind of present it with my collaborators on the display here. Thank you very much.
Thank you, Professor Kim, for the enlightening presentation. Okay, it's time for questions. Please, if you have any question, please raise your hand. We have several microphones are ready. Yes.
Thank you very much for the fantastic talk, as usual. And I watched it during the last 20 years, and the splendid development of this graphene and 2D materials physics. As a physicist, I enjoyed it a lot. But if you look at this audience, there are very, very few people who can really understand all of the concepts that you presented. And then the conference is something about the perspective on the quantum technologies. So my question is a little bit general question that, for example, in the time span of like 10 years from now, what is the most important quantum technological perspective you have on these 2D boundary bars materials?
Yeah, okay, so that's a fair question, and then difficult questions to answer. But also, it is probably more personal perspective. I think that, to me, the most exciting part is the possibility of creating very unusual quasi-particles, such as anyons, right? There are many kind of platforms that I just kind of went through. So quantum platform, quantum plus the superconductors, maybe some of these the unusual excitons, and there are a few others that possibility. But is there a way that we can create this unusual quasi-particle, especially some sort of anyons or non-abelian anyons, whatever, right? And if you have those kind of material platform, and we can just manipulate them with, and they are kind of remain as robust, I think there are kind of rather exciting devices can be formed. I think, for example, the proposal of the topologically protected qubits based on the topological superconductor, defects in the topological superconductor, I would say. That's, I think, fascinating opportunity. I think 2D materials and their van der Waals system is really well positioned to just attack that problem. I hope that is kind of basically essential part of the message that I wish to deliver.
Okay, maybe one more question? Yes. Oh, over here.
Yeah, just a quick question on the BC-BCS crossover.
Yeah.
So the second part, I understood better the analogy to the cold atom experiments with the B-field tuning in the Landau levels, where you really control the pair size also through the B-field. But
yeah.
Initially you mentioned there were predictions how to tune it with density, and that I didn't understand so well, because
Yes,
there I
yeah.
didn't see how you're controlling the pair size. Can you
Right.
explain how that
Yeah,
works?
it's good. So it's a little bit different from the cold atom in the following way. So usually this exton is interlay exton. Electron is top and bottom. So you can, if you ask what is size of exton, there are two different sizes. One is the size, basically what is the separation between the electron hole. So that's kind of often the layer separation, or often that in jargon D. And the other length scale is the distance between the exciton. So that's kind of exciton density. In the magnetic exciton, that exciton density is controlled by the magnetic field, because that's basically magnetic length. So when I just increase the magnetic field, that magnetic length becomes small, that you can just view as this is the way that we have the more exciton kind of plug in. That's why when you look at this phase diagram, temperature versus magnetic field, and this B field is what we call control the density of the exciton. Size of exciton is more like the kind of closely related the separation of these two layer D. So many things that present here can be scaled with this dimensionless parameter, so-called D over L, where L is basically magnetic length. So then mapping is kind of can be done. It's a little bit of simplification, because you can still have this is anisotropic system. So you can just think about what is the lateral size of the exciton itself. So often that comes also the correction of the scaling of the D over L.
Okay, thank you for those nice questions. And once again, thank you, Professor Kim, for your presentation and answers.
Thank you.
Okay. Now let's move on to our